Okay, I think we can start. This is lecture 20 of the course, the second last lecture. Okay, so whenever we study galaxy evolution, one of the sort of most straightforward observational questions you can ask is, at some given stellar mass, how do star formation, morphology, and environment depend on each other? Okay? So pick a stellar mass. So you may say, I will pick only massive galaxies, more massive than say 10 raised to 10 solar masses. Then what is the interrelationship between star formation rate, morphology, and environment? So these are the three sort of interconnected parameters in galaxy evolution. So some years ago, my PhD student Omkar did a very comprehensive study of this question. In fact, this was the central question of his PhD thesis. So he first asked the question, how does star formation depend on morphology? And what is shown here is the contour of density contour of his sample. What's plotted on the x-axis is log of m star, this log of the stellar mass, and on the y-axis is plotted the log of the specific star formation rate. Specific star formation rate is simply the star formation rate normalized by the stellar mass. So solar masses per year divided by solar masses. So it has units of per year. And of course, high SSFR means you are highly star forming. Low SSFR means you're not forming too many stars. So you can divide the space into three regions. Above this line is what are called the star forming galaxies. Then in between are your green valley galaxies, and here are your quenched galaxies. While doing this, we did not give consideration to morphology. So for this particular panel contains galaxies of all morphologies, but they are all of fixed stellar mass. So they are all between about 10 raised to 10 to 10 raised to 11 solar masses in stellar mass. How were these quantities obtained? Through stellar population synthesis modeling. So we carried out stellar population synthesis modeling of 8,000 galaxies, and we measured the star formation rate, the stellar mass, specific star formation rate, etc. for all of them. So this plot was constructed after that. So clearly there are two regions. Okay, if you separate it in terms, not in terms of specific star formation rate, but in terms of color of the galaxy, you would call this as the blue cloud, and you would call this as the red sequence, etc., which we saw last time. But now, if you separate them by morphology, so these are the late type spirals. They are mostly here. They're mostly star forming. The early type spirals, ETS, are also mostly star forming, but there are a few quenched early type spirals. The moment you transition to S0, now the center of gravity is sort of shifted down. So the dominant population now is over here, which is the quenched population. But there are some S0s which are star forming still. And here, you go now to ellipticals. So although there are a few star forming ellipticals here, most of the ellipticals are quenched. So clearly there is a movement downwards of the population as you go from late type spirals to ellipticals. Very, very clear dependence on morphology. Omkar's paper, yes. That's his surname. Okay, so this is another thing from Omkar's paper. So now we say that, okay, let's represent this same idea in a different way. Let us see how the fraction of galaxies changes between the star forming green valley and quenched regions. Okay, so this blue curve represents late type spirals. So they are quite dominant in the star forming region, and within the star forming region itself, they begin to fall and go to nearly zero here. Whereas if you take ellipticals, okay, which are these, they are nearly zero in the quenched, in the star forming region. In the green valley, they go up and they go stay high up in the quenched region. And S0s are somewhere in between. Over here, what seems to be what is happening in the green valley is a dramatic decrease in the population of fraction of early type spirals, and a corresponding dramatic increase in the number of S0s as well as in the number of ellipticals. So clearly, the green valley is representing some kind of transition between the early type spirals and the latest. Now, these are not differentiated by environment. There are galaxies of all kinds of environments. So there are cluster galaxies. And in clusters, we already know that this sort of thing is expected. That because of ram pressure stripping, the spirals are going to get transformed into S0s, or S0s further may get transformed into ellipticals. But there are some curious things. For example, the population of S0 galaxies. It's here, it goes down as expected, but over here it goes up. So there is a population, a small population of star forming, highly star forming S0s. So there are some future work we did on this, which tried to identify what these are. Okay, are these fading spirals or rejuvenated S0s? It turns out that many of them are rejuvenated S0s. So these S0s sometimes undergo a merger with a gas-rich, minor merger with a gas-rich galaxy. So that leads to a burst of star formation. So for some time, they have a very high SSFR, some of them. Right. Now you ask the question, how does morphology depend on environment? In every class, there are at least 1,000 galaxies in each class, but not in each bin. So there are about 10 bins. So in each bin, you may have 100 or even fewer than that. In some classes like the early type spirals and so on, you have a lot of galaxies. In general, the size of the error bar, the vertical size of the error bar is an indicator of how many galaxies there are. So this is like a Poisson fluctuation on the numbers. So if the error bar is large, for example, here error bar is large, that means that the number is quite small. Whereas here error bar is quite small, that means the number is large. So it varies in every bin, in every class, it's somewhat different, but there are a lot of galaxies, so we were able to do this. Now we say, let's slice it by environment. So now what you see that as you go to higher densities, early type spirals goes down, fraction of ellipticals goes up, fraction of late types spiral goes down. But what we found, at least for our sample, the spiral of fraction of S0s increases initially, but then stays roughly constant. Within the error bars, it's constant. So this is your morphology density relation in action, that as you go to higher surface densities, the fraction of early type galaxies, ellipticals, S0s is high, and the fraction of spirals is small. And the reverse is true if you're looking at low galaxy densities. Now this corresponds to almost to field galaxies, and this corresponds to fairly rich clusters. There is in log space 4 orders of magnitude, not in log space, in real space, there's 4 orders of magnitude difference in the galaxy density between these two ends. This is the projected surface density. This is the fifth neighbor distance. Yes, yes. So there are all kinds of biases. It's not a, huh? Because you can't select fainter than that. You're not complete. 2 magnitudes fainter than your flux limit. So you don't have any information. You can put any limit, I'll go up to magnitude 30, but if you don't have the sensitivity, you're not going to detect that galaxy. Yes. So
there is also a range in Z also.
Okay. Yes, because Z range will be narrow or it will be low redshift because you can't detect galaxies at high redshift, faint galaxies at high redshift. So what you do is you try to cheat. The Malmquist bias hits you, whatever you do. You try to mitigate its effect by restricting yourself to a region of space, parameter space, where the Malmquist bias is not severe. It's there, but it's mild. You live with that. You don't go to try and detect very low luminosity galaxies at high redshift. That is impossible. Right. Yeah. So, yeah. Yes. Yes. No, we don't. Why would you? The maximum luminosity galaxies will always get detected. You may be affected by strong cosmic variance. So for example, if you sample only a small volume, like if you say, I will go only up to redshift 0.1, and if you are selecting, if you are studying quasars, for example, you will find 0 quasars in that redshift range. So you can't study quasars. So then you relax your criteria. You cannot do better, or you go fainter. So people do both of those things, which is you either try to estimate the extent of the bias by going fainter, or you correct for that bias in some way by V over V max correction or some other form of statistical correction.
Also, because we are taking the projected density. So
yes.
If there should be a large range of jet, then that projection is some galaxies will be for this jet is hanging in the large range.
Yes.
So
no. So when you do the second, third nearest neighbor, okay, fifth nearest neighbor, you try to do it in 3-dimensional space. You don't try to do it usually in 2D. So you do it in 3D. So then there's no problem. Suppose there's something by chance lying at some higher redshift or low redshift.
We don't have any problem in large jet, but we are doing a projection. So if the jet will be very large,
yes,
then there will be.
That is true. That is true.
So I get projected then.
You can get biased. You can get biased.
Yeah.
Correct. At lower redshifts, you try to estimate the peculiar velocities. So maybe I should. Yeah. See the peculiar velocities. What are the typical peculiar velocities? Even in high mass clusters, you have peculiar velocities of the order of 1,000 or 1,500 kilometers per second, not more than that. You cannot have peculiar velocity of 10,000 kilometers per second. That's that. So that's your speed. Now, at what redshift will you get the peculiar velocity dominating over the cosmological velocity? Okay, for at low redshifts, you know that redshift is just V by C, correct? Now, if it is V by C, at 3,000 kilometers per second, you will get at what redshift? 0.01. Okay, so at very, very nearby objects only, the peculiar velocity can dominate the. So in the local group, it can. If you're looking at Andromeda, yes, it can. If you're moment you go a little bit, 0.01 is not a high redshift, very low redshift. Moment you go beyond that, the cosmological redshift begins to dominate over the peculiar. But still, when you're observing a cluster, you need to get the peculiar velocities right. So what you do, what is very often done, is that suppose I have a cluster of galaxies. I don't know the peculiar velocity of any galaxy. What I try to do is that I try to identify the brightest cluster galaxy. And I assume it's sitting at the center of the potential well. So that is not moving. Other galaxies are moving around it. So I fix that. I find its cosmological redshift. Okay. Once I know the cosmological redshift of that, I can find the peculiar velocities of every other galaxy in the cluster. But now suppose I don't even know whether a particular galaxy is in the cluster or not. Right? It may be just outside the cluster. It can't be way outside. So if the peculiar velocity is different, is coming out as 10,000 kilometers per second, I have to say, no, that can't be correct. This galaxy is actually at high redshift, and therefore it is showing high. This is not a member of the cluster. I can throw it up. But if there's a cluster here and just behind it is your contaminant galaxy. It's not a member of that cluster, but it is showing up over here. Right? So its peculiar velocity will be consistent with zero velocity. Right? Because it won't be moving, the cosmological redshift will be the same. Now what you do is you take your sample of galaxies, and then by your modeled peculiar velocities, you try to compute the mass of the cluster. Once you compute the mass of the cluster, you try to compute what should be the peculiar velocities given the projected distance from the center, etc. See if it is consistent. For galaxies that are true members of the cluster, the mass computed from the velocities and the velocities computed from the mass will be consistent with each other. For galaxies which are not in the cluster, they'll give inconsistent values. So the measured peculiar or the modeled peculiar velocity is, let's say, 500 kilometers per second. But the mass tells me that this particular galaxy needs to have a velocity of 1700 kilometers per second. Then I say, no, something is wrong. Probably this galaxy is not a member of the cluster. I take it out. Then I use the velocities to recompute the mass of the remaining galaxies to the virial theorem to recompute the mass, use that mass to predict the velocities and see everything is consistent. Once you obtain closure in this loop, then you say that, okay, this particular galaxy is a member of this cluster. It is therefore at the same cosmological redshift, and therefore it has this exact peculiar velocity and so on. So it's an exercise. It's not a simple calculation. It's an iterative exercise that can be done, has been done for all the Sloan galaxies. So every galaxy is now classified as, okay, this particular galaxy is a member of a group of 5 galaxies. These are the other 4 galaxies, and this is the peculiar velocity, and this is the cosmological redshift of this group, etc. Everything is known. Okay. So feedback. So the sun is 8.5 kiloparsecs away from the center of the Milky Way, which itself is 30 kiloparsecs in length, but it has a thickness of only 0.3 kiloparsec. Very thin, long disk, about 100 times as long as it is thick. Because it is so thin, what can happen is what are called referred to as galactic fountains. Okay, they can be bidirectional also, but in most cases the star would be lying closer to one side of the disk, either on the upper side or on the lower side. So that creates, so whenever it goes off as a supernova, this particular star will create a emission, a fountain like this. So gas and dust and material will get thrown out, but it is also getting attracted by the gravity of the galaxy. So after some time, there will be a fallback. Again, that gas will slowly settle into the disk. So this is referred to as the galactic fountain model. And this is responsible for energy transport into the halo. This sustains the hot halo. Remember we said last time that we have discovered a hot X-ray emitting halo around the Milky Way. It is phenomena like this, which are constantly supernova getting generated every few hundred years in the Milky Way disk, that are constantly transporting energy into the halo and keeping it hot. Because without that, the cooling of the gas will over time dissipate the halo. It can be bidirectional also, but it will have more domination on the side in which there is less density of material. Okay, so they should have shown a few of them at least two-sided. Okay, but they've shown them as one-sided in this cartoon illustration. Why is it more collimated? Why does it become more diffuse as it goes out? So what happens is there are these sort of breakout regions. In the thin disk, the material is sufficiently thick that that isotropic explosion gets mitigated in some directions because there's a lot of density of material around the disk. So for example, it never spreads in this lateral direction. And remember, it's not very collimated. Okay, don't think of this like a radio jet or a pulsar beam or anything like that. I mean, this may be, this is 8.5 kiloparsecs. So it may be 10 parsecs, 20 parsecs wide. But the reason why it's not spreading out along the disk direction is because the disk is thick with material, with density. So the energy of the explosion can escape only in a direction perpendicular to the disk. And later on it diffuses because it loses energy also. It's losing energy as it travels, but it's also losing energy continuously because of the gravity of the galactic disk. Right? The disk is pulling it back. This thing happens, according to the model, happens due to supernova, but it can happen if the supermassive black hole turns active. Then these kind of ejections become very, very common. I mean, very, very powerful, but for a very low duty cycle. So in the case of the AGN, when the AGN is on, it will dominate the supernova explosions. Right now, the AGN is off. So the supernova explosions are dominating for the Milky Way. But if you have an active galaxy, this will be minor compared to the effect of the AGN. So now this is also going to lead to metallicity, circulation and mixing. Okay, so the high metallicity gas from the disk is getting expelled, right? So if you measure the metallicity of this gas, it will be high because it is already reprocessed in the disk. Okay. So now we spoke of bulges in spiral galaxies or disk galaxies as miniature versions of elliptical galaxies in almost every way, right? We said they have an old stellar population, they don't have much gas, they're not actively forming stars, they follow the Divoculars or Circic profile, etc. But some years ago, it was discovered that there are two kinds of bulges. There is one kind which we refer to as classical bulges, which are seen in the top three images over here. These classical bulges are actually like little ellipticals sitting at the center of the disk galaxy. But there is another class of bulges which are called pseudobulges. So this is a nice example of that. That photometric component is not cleanly separated. Okay, it just seems to be brighter near the center, right? There is no obvious second component of the bulge. Similarly over here and over here, although it's only in this galaxy that it becomes very obvious. These type of bulges are referred to as pseudobulges. And this kind of bulge is fundamentally different from this kind of bulge, not only in its properties, but also in its formation. So it is believed that these kind of bulges arise due to secular evolution processes. Okay, whereas these kind of bulges arise primordially. So you can think of this as a small elliptical which has acquired a large disk. You should think of this as the reverse, a disk galaxy that has grown a bulge. And how has it grown a bulge? If there is instability in the disk, that tends to form a bar-like structure, a stellar bar. And stellar bars are very efficient in funneling gas from the outskirts of the galaxy towards the center. And because of that, star formation near the center increases, and that leads to the creation of a bulge. So now if you see this, these two, there should be a systematic difference in their stellar population. So if you take the mean stellar age of these stars and the mean stellar age of these stars, which one will have a higher stellar age? This one, upper one. Okay, so they're like ellipticals, they form their stars very early. These are ones which will have all kinds of ages. There will be 1 gigayear-old star, 2 gigayear, 3 gigayear, 5 gigayear, and so on. So you'll be able to manifest itself in this. So how do you identify them? Like from an image, the classical bulges tend to have a steep Cercic index. Pseudobulges tend to have a shallow Cercic index. So that Cercic value of n will be close to 4 or maybe even higher for classical bulges. For Cercic bulges, for pseudobulges is usually less than 2. So that's the way you see them. These classical bulges, it turns out, are common in early type spirals, SA and SB type galaxies. But in pseudobulges are more common in late type spirals. Classical bulges have old stellar population, and these have a mix of old and young stars. These formed like elliptical galaxies, and these formed through a process known as secular evolution. Secular evolution means an evolution that is independent of its environment. So the galaxy itself undergoes over time changes within its structure, which is independent of any other environmental effect, no mergers, no anything. In classical bulges, very often a stellar bar is absent, and in pseudobulges, it's very often present, and it plays an important role in the creation of the pseudobulge itself. Classical bulges are like elliptical galaxies, and therefore they follow the Coromandi relation and the fundamental plane, and pseudobulges do not, because they are not elliptical like systems. And if you differentiate by mass, then classical bulges are found in high mass galaxies, and pseudobulges are preferentially found in low mass galaxies. Although they're found, I mean, it's not a perfect clean separation, but predominantly. So clearly there seems, so whenever you have a galaxy formation model, now it should explain the formation of classical bulges and the formation of pseudobulges separately in the right proportion, as a function of mass and as a function of environment. So there are a lot of sort of unanswered questions. How does pseudo classical occurrence depend on the environment? Are there stellar ages correlated with the disk? Why are classical bulges more common in S0 galaxies than pseudobulges, etc.? These are questions that were asked and answered by Pritish Mishra in his thesis. So these are the 3 papers that each of them answers one of those questions. Okay, so now we are ready to move on to formation mechanisms for ellipticals and spirals. So in a very influential paper written in 1962, again Lynden Bell and Sandage came up with a model in which galaxies form from the collapse of gas clouds, and suggested that the difference between ellipticals and spirals reflects the rapidity of star formation during this collapse. In the ELS model, as it's called, again Lynden Bell and Sandage, in the ELS model, ellipticals formed by a gigantic gas cloud collapsing under its own gravity, but also fragmenting, because what happened was within the gas cloud, certain overdense regions also they had a runaway collapse, and they collapsed and formed individual stars or individual star clusters, right? And so this kind of thing happened at high redshifts early on in the universe, and it occurred in regions, as we have seen, where the overdensity of matter and dark matter was highest. If this happens very rapidly, if most of the gas turn into stars even before they fall in, this kind of fragmented collapse, if it happens, then by the time the possibility of collision comes in, almost all the gas has been converted into stars. What will happen then? Collisions are unlikely. So the process becomes dissipationless. No energy is lost, just a trade-off between kinetic energy and potential energy. And these infall motions are converted into the random motions of stars, resulting in elliptical, in those sort of random orbits and elliptical galaxy. If the cloud remains gaseous during the collapse, which means it doesn't fragment and immediately form stars, then the gravitational energy can be dissipated. It's no longer dissipationless via shocks and radiative cooling of the gas. In this case, the cloud continues shrinking slowly without forming too many stars at one go, until it reaches a stage. Remember, the cloud, the dark matter halo in which it forms, has some angular momentum, and therefore the baryons also have some angular momentum. That angular momentum builds up, and the cloud shrinks until it gets supported by the rotational angular momentum of the gas. And that leads to a formation of a rotationally supported gas disk, which then slowly forms stars. So it slowly converts gas into stars. So Milky Way, for example, has been a gas-rich disk for a fairly long time, and it is slowly burning up, using up the gas and converting it into stars. It is believed that the most massive spirals have formed in this way. So when you talk of galaxy formation, actually the word galaxy formation is very misleading, because galaxy formation is not an event. Galaxy formation is a process, right? You cannot say that, okay, today galaxy has formed, because then it's just one star cluster, and tomorrow it merges with another star cluster, forms a bigger galaxy, or converts more gas into stars. When do you say a galaxy has formed? There's no specific event you can specify. So you think of galaxy formation as a process. And since galaxy evolution is also a process, it's very hard to distinguish between galaxy formation and evolution. So when I say galaxy formation, sometimes I almost always I mean evolution, or the early stages of evolution I call as galaxy formation. So it has two principal aspects. First is the assembly of the mass, so getting sufficient gas together in one place, and conversion of the gas into stars. This must be related to the large-scale hierarchical structure formation, plus the dissipative processes, which are much more complicated, as we have seen, compared to the growth of the large-scale structure, which is a purely dark matter gravity-driven process. No problem. We understand that very well through simulations. We know from the Magorian relationship, which is the relationship between the bulge mass and the central supermassive black hole mass, that the formation of the massive supermassive black holes is also related to the formation of the galaxy as a whole, the bulge as a whole. Generally, we think of massive galaxy formation at high redshifts. So the progenitors of today's massive galaxies were the highly star-forming galaxies at high redshift, but dwarfs are still forming now. So this is referred to as cosmic downsizing. As you go further and further in time, the dominant place where star formation is happening in lower and lower mass galaxies. Observations have found populations of what must be young galaxies, which are the ostensible progenitors of large galaxies today at high redshift. If you want to go beyond that, redshift 7 and beyond, that really is the JWST frontier. And we go into what is called as the reionization epoch, reionization era. If you look at galaxy formation timeline from the star formation perspective, the smallest scale density fluctuations keep collapsing, with baryons falling into the potential wells dominated by the dark matter, achieving high densities through cooling. So now cooling is a very, very fundamental process for the formation of stars. If that cooling can be prevented, okay? So for example, cooling is more efficient when at higher densities than it has at lower densities, because you can have other modes of cooling at high densities, conduction or convection and things like that. If you have very low densities, you can only have radiative cooling. This process, the cooling process, starts right after recombination. Once the gas densities are high enough, star formation ignites. We don't know when, we'll know with the JWST, but probably around redshift of 20 or 30. And by Z equal to 6, we know by studying the spectrum of distant quasars that the UV radiation from stars in young galaxies has reionized the universe. These protogalactic elements of stars and gas keep merging, forming larger objects in a hierarchical fashion. During this, star formation enriches the gas, and some of it is expelled into the intergalactic medium, primarily through supernova explosions, while more gas keeps falling in because of gravity. If a central massive black hole forms, the energy release from this can create considerable feedback. Now, it is not just the baryonic matter which is evolving with time. The dark matter halos are also evolving. So this is from a very important review paper by Barkana and Loeb in 2001, where they studied sort of the current understanding at that time of dark matter only simulations. And these simulations invariably show that the dark matter mass function also evolves with time. Okay, so these are, I don't remember what exactly these time slices correspond to, but every curve corresponds to a different instance in time of the dark matter mass function. Can you tell me which must represent a later time? Which curve? Yeah, probably the red one or the magenta one. They have to be later times because you don't form high mass halos before that. Okay. So these halos, so just like galaxies can merge, the halos can merge too. When halos may or may not contain galaxies. Each halo may contain more than one galaxy. If that is the case, one refers to the galaxy at the center of the halo as the central galaxy, and any other galaxies as satellite galaxies. You then say that the satellite galaxies sit within a sub-halo in the halo. So if you plot the density distribution, it's sort of going down from the center, but wherever there is a sub-halo, there will be another small peak corresponding to the sub-halo. So if you see this, so this galaxy would be a central. It is sitting in its own sub-halo, and this is the overall halo of this group of galaxies. And these are smaller galaxies which are all sitting in their individual sub-halos. So I said I put missing in bracket because one of the problem with the early simulations was that there was the missing satellite problem. which meant that the simulations were showing lots of little galaxies, right? And those were not seen. They just didn't seem to exist. So what could be a reason why there was, the simulations are showing small galaxies, but when you observe a group or a cluster of galaxies, you don't see that many small galaxies. Sorry? Flux limit is one problem, but they said, okay, we'll go deeper.
The density is so small that it is averaging out.
What do you mean averaging out?
The resolution might be limited because they are small.
Yeah, they're small, no, but people said that, okay, we'll just look at nearby groups and galaxies. In the simulations, we are predicting so many galaxies of, let's say, mass 10 raised to 7 to 10 raised to 8. Suppose 10 galaxies are predicted, I see only one. They're merged, but what's much more likely is that the feedback has been incorrectly modeled in your simulations. Sometimes not modeled at all. So that was with the early simulations. So if the feedback is stronger than what you think it is, for example, if the supernova rate is higher than what you expect, in very small galaxies, they begin to form stars, but one supernova goes off and it just throws out all the gas. It completely destroys that galaxy. So then there's nothing left. There are a few stars hanging around. That's not a galaxy. Low mass stars are there. And that's why you can't detect it. So if the feedback is underestimated, then the missing galaxies problem emerges. If you put in the correct amount of feedback, then the missing satellite galaxy problem goes away. So right now, so 20 years ago, this was a big area of research. Now people have sort of accepted that feedback is sufficiently strong, and that this may not be a thing, and the potentials are very small. See, if a supernova goes off in the very early stages of a galaxy, then it can completely disrupt things. The galaxy just disappears. Okay, yeah. It's a little bit of a circular problem. It is not, there is no fundamental principle that tells you that so many galaxies. You just run a simulation, you see them. In many of these simulations, feedback is implemented not as of in terms of fundamental physics, but in terms of a knob that you turn. Okay, punch so much energy into the ISM, see what happens. So it's completely phenomenological approach. It is not fundamental physics type approach, and that is primarily because we don't know. You check for consistency. See, if you have formed 10 stars and you require 100 supernovae to disrupt it, then obviously that is checked for. The IMF is checked that it's reasonable. The supernova rate has to be reasonable, but within the boundaries of reasonability, it is tweaked as per fancy. Nowadays, people have much better simulation where the feedback is modeled in a much better way. But eventually, everything is parameterized as a feedback. So you change it, you make your simulation, you compare with observations. Okay, I got this time I got 4 satellite galaxies. I want only one. I'll turn the knob in my simulation till I get one. Yeah, it is believed that each galaxy sits in its own halo. Okay, a halo may have no galaxy, but each galaxy must sit in a dark matter halo because it has to form only in a region where there's sufficient dark matter gravitational potential. Now, whether you call it halo, mini halo, sub halo, etc., etc., that's a matter of detail that you will have to define in your book or paper or whatever you're writing. But what this picture shows is broadly correct, that every galaxy is sitting in its own sort of sub-halo, and the whole group is sitting in one larger halo. And if it were a cluster, then there may be one larger halo in which it sits. So now one important question to ask is, can baryonic properties be determined by the properties of the dark matter halo? And Asim has a very interesting paper some years ago on this. And there are two schools of thought. There are people who say that the simulations are now good enough that what you do is that you make the simulation and you compare that in my simulation, okay, this 10 raised to 11 stellar mass galaxies are sitting in this kind of halo with these properties. Therefore, your 10 raised to 11 galaxy in a similar environment, etc., must be sitting in a similar kind of halo. And therefore, I can say that your halo's properties are known. And once I make that mapping between the halo property and the observed property, then I can make predictions about the baryonic properties by just determining the properties of the dark matter halo. So the dark matter halos has all the classical mechanics types properties that you can imagine. Dark matter halo has mass, it has a certain characteristic size, it has a mass distribution, it has angular momentum, and so on. So, and therefore it has experiences gravity as per Newton's laws, all that. So since the properties of the dark matter halo are completely determined by the simulations, if you can map this onto real observations, then it becomes very easy to model the dark matter properties of galaxies. And some people like Asim believe that we have now reached that stage with the simulations. Some other people feel that no, not yet. Maybe in 5 or 10 years we'll reach that stage. So this is how halos grow. So this is called as a halo merger tree diagram. This is a hierarchical bottom to up growth. So let's say you have this particular halo today, right? It was formed by the merger of these two halos, and in turn these halos were formed by the merger of lower mass halos. Okay, the halos here, for example, this halo came to this halo, you'll see that it has become slightly larger in size because a halo need not merge with other halo to grow in mass. Okay, it can also accrete mass from the surrounding intergalactic medium or whatever. So just like galaxies accrete gas from the intergalactic medium, halos can also attract dark matter or baryonic mass from around them. And of course, when two halos merge, the galaxies then move into the same bigger halo. There they may merge or they may just interact and continue in some orbit around each other. So eventually you will form a very large halo. This process is irreversible. You can go from a small halo to a big halo. You cannot go from a big halo to a small halo. So this is something we've seen already. The semi-analytic galaxy evolution simulations, semi-analytic models, as well as full-scale hydrodynamic simulations are now able to reproduce the observed universe quite well. Okay. Galaxy formation is obviously a much messier problem than structure formation. Because we have to understand the relatively poorly understood baryonic processes. And there are many baryonic processes. It's not just one process, not just star formation, or not just supernova evolution or whatever. All of these things are complex physics. The shock heating of the gas that leads to overdensities, which if the gas subsequently cools can form stars. The cooling of gas inside in the dark halos. The formation of stars, that surprisingly is a relatively less well understood process. exactly how do, given a certain amount of cold gas at a certain density, temperature, pressure, how do stars form? That is not precisely understood. The evolution of the resulting stellar population, this is now very well understood. That's why stellar population synthesis works, except for the post-AGB phase of stellar evolution. Feedback processes generated by the ejection of mass and energy from evolving stars. So this is uncertain, all your supernova rate or stellar winds and things like that. Production and mixing of heavy elements, the chemical evolution that we looked at in the closed box model, that also is poorly understood. The effects of dust obscuration are also uncertain because we don't know how much dust gets formed and we don't know how that dust is distributed and at where is it distributed. Is it close to the stars or is it far away from the stars? And the formation of black holes at the galaxy centers and the subsequent AGN that get formed, these also lead to a lot of uncertainties. If you look at an individual galaxy, you can think of the interplay between the various components in the following way. So there is hot gas that may undergo cooling, become cold gas, and that cold gas may give rise to stars. The stars themselves may evolve. If there is a supermassive black hole, the stars could be eaten up by the supermassive black hole or tidally torn up. Okay. The hot gas itself could fall into the SMBH. The cold gas could turn into hot gas when it approaches the SMBH and then fall into it. So AGN accretion will have an effect. AGN accretion will also have feedback. So here on this side are all the feedback processes: feedback of energy, feedback of mass, feedback of metals. All of these are happening with all the components of the galaxy. So if the AGN goes off, it will lead to feedback of gas, metal-rich gas, lead to feedback of energy and so on. And this, obviously, this whole thing is not a closed box. There is inflow from outside. This may be in the form of gas, which is accreting onto the galaxy, or it could be a galaxy itself coming in and merging. And there are outflows. The outflows are all kinds of gas and stuff, plasma that's flowing out of the galaxy. So these processes are all interconnected, interrelated, and much of the study of galaxy evolution is focused on understanding different aspects of this diagram and the interrelationship with each other. SMBH will drive energy into the SMBH means the accretion disk, not the black hole itself, but the accretion disk that forms around it and the AGN phenomenon. That is what is driving the feedback. And some of these processes are two-way. For example, this cold gas. Okay, cold gas may flow this way or it may flow in. Okay. So this we've already looked at. I think we, but again, this is another view of the same thing. So if you know gas dynamics, evolution of dark matter halos, primordial fluctuations, star formation and feedback, the stellar population. So if you have your population synthesis model and you have your cosmological simulation, then you can add a semi-analytic model and predict all of these things. Nowadays, they've tried to replace the semi-analytic model with full hydrodynamic simulations, so you don't have to worry about it. So this, okay, it's probably one can skip this. Let's go straight away to the flowchart. So this is a very nice flowchart which summarizes all of galaxy formation in one plot. Okay, so you have some initial and boundary conditions. We've studied the CMB, we know what those are. Then gravitational instabilities will lead to formation of dark matter halos, which will have dark matter, but also gas falling into the halo due to its gravity. Then there are two scenarios. One is that the cooling of gas is very efficient, and where cooling is not efficient. If cooling is effective, then you have two situations. The gas has large angular momentum or not. Okay, if it doesn't have large angular momentum, you can have a starburst thing, maybe dissipative or perhaps dissipation less also. But if you have large angular momentum, then you lead to a formation of a gaseous disk, which leads to star formation and eventually a disk galaxy. The disk galaxy can undergo a major merger or not. If it doesn't undergo a major merger and the disk itself is massive, then you can have bar instabilities forming, inflow of gas driven by that bar instability, maybe the triggering of an AGN, because the moment you drive a lot of gas close to the supermassive black hole, you'll have the AGN turning on. And that leads to the formation of, that leads to the growth of the supermassive black hole, but also leads to the growth of the central bulge. And you get a bulge disk system at the end of it. If the disk is not massive at all, then you could have a simple disk which has lots of gas and is forming, slowly forming stars. If you go this way, if the cooling is not effective, if there is further merger and accretion, yes, then basically the dark halo and the baryonic mass content continues increasing. But if there is no further mergers, you may just have a situation where a hot halo forms and the galaxy is unable to grow in size because it's forming stars within it. It's providing enough feedback to maintain its hot X-ray halo, but no further cold mode accretion is possible, and therefore growth stops, at least for some time, till the hot halo dissipates. If you go this way, starbursts, now if you do a major merger with a gas-rich galaxy, yes, then you get a starburst, AGN, perhaps tidal tails, and so on. And if it's not a gas-rich galaxy, you get a tidal tail, only a tidal tail. Why? What does the tidal tail contain? Tidal tail contains stars usually. Okay, not much gas. So, so the tail is basically stars that have been stripped out of the one of the two galaxies that are interacting, and so it's a tidal effect. Whereas if it's gas rich, then more stars can form. So all of these can lead to a high entropy system, some kind of spheroidal system. This early starburst can also lead to a spheroidal system. If that spheroidal system undergoes some kind of gas accretion, then it can acquire a disk. Okay, so maybe it becomes a S0 galaxy. If there is no gas, further gas accretion, and you only have those initial stars that form, then you lead to an elliptical. So this is how what forms ellipticals. This forms maybe S0s or some kind of spirals. This is a disk only galaxy. Okay? So all of these things are operating at different levels in different kinds of galaxies. And what people are trying to work out is which boxes are important, which boxes are not important. They're also trying to work out whether all these connections are correct. Maybe there are some arrows here which have not been drawn, which need to be drawn. Maybe there are some arrows which have been drawn, which are not necessary. They're very rare cases. They can be removed. So modifying this sort of flowchart seems to be the exercise of most people doing galaxy evolution. I think somewhere between 500 to 1,000 researchers worldwide are basically working on this. And this is a plot that I showed in the first lecture. So this is another representation. So just like, so what seems to really decide this versus this seems to be the speed with which the star formation happens. If the star formation is very rapid, you will end up somewhere here. If the star formation is not rapid, it's slow, you will end up here. This is a sort of high entropy situation, or low entropy situation, low net angular momentum, high net angular momentum, and so on. So there are trends with the physical properties, but what seems to be important is fast versus slow processes, and whether the environment is important or not, whether interactions, mergers, harassment, etc., whether they play an important role or not. If they do, then you get one class of objects. If they don't, you get another class of objects. And all of these seem to have smaller effects. Your star formation, gas recycling, metal enrichment, energy feedback by supernovae, and so on. What seems to be more important is whether the environment led to internal or external effects, or whether the processes were fast or slow. Okay, so this is a slide taken from a review article by Kornmendi and Kennicott, which talks extensively also about classical and pseudobulges and things like that, and their role in this process. So that's it. I will stop and take any questions. Maybe I should leave this slide. So this diagram is taken by a textbook from a textbook by Moe et al. So Moe, Vanden Bosch, and White have this nice text on galaxy formation and evolution. It's one of the more recent textbooks. It's quite well written, big textbook, but it explains even aspects which I have not covered, like for example, the formation of the dark matter halos and their evolution,